The NASA Voyager probes, launched in 1977, were originally designed to study Jupiter, Saturn, and their moons. However, they exceeded expectations by accomplishing their primary goals within 4 years. NASA then extended the mission to include the outer planets Uranus and Neptune. After that, the Voyager interstellar mission was launched with the aim of exploring beyond the outer boundaries of the Sun's influence. Remarkably, even after nearly 45 years, NASA continues to receive commands and transmit valuable data back to Earth's deep space network, making Voyager the longest-running mission in space exploration history. Voyager I, after 45 years, is currently located a staggering 24 billion kilometers away from Earth, which is more than 29 times the distance it traveled from Earth to Jupiter initially. In 1990, after completing its mission to the gas giants, the cameras on both probes were deactivated to conserve power. Because, like many spacecraft, Voyager I is powered by an RTG, radioisotope thermoelectric generator, that converts heat from radioactive material into electricity. However, the power output of the RTG decreases by about 4 watts every year, and currently Voyager I is only producing 57% of its initial power. NASA shut down various instruments on board Voyager I and removed the software responsible for operating the camera to save memory. The computers and software used on Earth to analyze the images are no longer in existence. Furthermore, the cameras and their heaters, exposed to the harsh conditions of outer space for several decades, likely won't be functional anymore. The last image taken by Voyager I is the iconic pale blue dot photograph of Earth, captured from a distance of around 6 billion kilometers, making it the most distant image of Earth ever recorded. It's sad we won't see Voyager I's images again, but it's nice to know it'll be out there, like a memorial of humanity's achievements. Assuming the cameras on Voyager I were still in good condition, what would they capture if they were turned back on? Many people assume that Voyager I, being so far from the Sun, would be in complete darkness. However, this is not true. Despite being 23 billion kilometers away, the sunlight is still 16 times brighter than moonlight on Earth, so it's definitely enough to play a game of chess. Images would appear dark, but we would still see the Sun and some planets as tiny faint pixels. Perhaps the most astounding fact is that despite the vast distance, the star constellations in our sky would appear exactly the same. To witness a significant shift in the stars and gain a different perspective of our galaxy, Voyager I would need to travel thousands of light years. However, the initial mission to the gas giants was just the beginning of the extraordinary Voyager journeys. To venture into interstellar space, the probes had to navigate through various challenging regions. First, they encountered the termination shock, where the supersonic solar winds collided with the opposing interstellar wind, creating intense resistance. Beyond this, the Voyagers entered the heliosheath, where the solar winds slowed down and accumulated, resulting in higher density and temperature. Finally, they reached the heliopause, the ultimate boundary between the heliosphere and interstellar space. Surprisingly, the beginning of the interstellar medium does not mark the end of our solar system. In fact, it'll take approximately another 300 years for Voyager I to reach the Oort cloud, an enormous zone filled with countless icy objects encircling our solar system like a protective bubble. After that, it'll require an additional 30,000 years for Voyager I to journey beyond the Oort cloud and bid farewell to our solar system forever. You might be thinking, why do we talk about leaving the solar system after crossing the heliopause instead of going through the Oort cloud, even though the Oort cloud is part of the solar system? Well, the reason is that the heliopause is the boundary between the solar system and outer space, while the Oort cloud is still part of the solar system. When a spacecraft crosses the heliopause, it means it's leaving the realm of the sun's influence and entering interstellar space. That's why Voyager I is considered to have reached interstellar space and left the solar system when it crossed the heliopause, even though it hasn't reached the Oort cloud yet. Crossing the heliopause is like crossing the border into a whole new cosmic neighborhood, while the Oort cloud is more like staying within the solar system's backyard. The Oort cloud is considered the outermost region of our solar system. The Oort cloud is a gigantic collection of icy objects like comets and rocks left over from the early days of the solar system. Sometimes these objects get kicked out of the cloud and go zooming towards the inner part of the solar system. Imagine if billions of rocks were heading towards Voyager I. Would there be a chance of them smacking into Voyager I? Well, entering the Oort cloud itself is pretty much impossible for Voyager I, because the Oort cloud stretches from about 1000 AU to 100,000 AU from the Sun. Voyager I is currently located at 125 AU. For the sake of curiosity, let's imagine that Voyager I enters the Oort cloud. In the Oort cloud, the average distance between comets is estimated to be around 16 astronomical units, AU. To put that in perspective, it's 16 times the distance between the Earth and the Sun, so we're talking about one comet every 2.4 billion kilometers. Now keep in mind that comets are actually quite small. Their nuclei have a diameter of around 10 kilometers, which is less than 0.1% of the Earth's diameter. To give you an idea, let's shrink a comet down to the size of a golf ball. If we scatter these golf balls around, the average distance between them would be about 10,000 kilometers. Now take the combined land masses of Eurasia and Africa and place a single golf ball somewhere, randomly. Next, fire a bullet randomly at the entire Eurasian-Africa landmass. What do you think the odds are that the bullet will hit the tiny golf ball? That's exactly how unlikely it would be for Voyager I to hit an Oort cloud comet on its journey out of the solar system. It's like shooting a bullet randomly at the entire Eurasian-African landmass and hoping it hits that one little golf ball. So, the chances of a collision are incredibly slim. When the Voyager ventured through the helios sheath, they stumbled upon something. You know how the Sun's magnetic field twirls in opposite directions at its north and south poles? Well, where these spins collide, it creates a ripple called the heliospheric current sheet, kind of like when you drop a stone in water and it forms rings. When this sheet reaches the termination shock, the edge of the Sun's influence, it gets squished like ripples crashing into a pool's edge. However, those squished ripples stack up and turn into magnetic bubbles. So, the boundary of the helios sheath isn't as smooth and straightforward as scientists believed. It's actually a wobbly and magnetically bubbly environment. This finding has completely rocked our previous understanding of the helios sheath. In 2012, Voyager I became the first human-made object to venture into interstellar space, leaving the Sun's heliosphere behind. It was traveling at an incredible speed of 540 million kilometers per year. Initially, NASA had doubts about whether Voyager I had truly crossed the heliopause into interstellar space. However, its plasma wave detector confirmed the transition with a significant increase in plasma density and galactic cosmic rays. The surprising part came when Voyager I detected no change in the magnetic field after crossing the heliopause. This contradicted theoretical models that predicted a magnetic shift in a region dominated by other stars' magnetic fields. NASA took nearly a year to officially announce Voyager I's interstellar achievement. Later, on November 5, 2018, Voyager II joined the Interstellar Club, traveling slightly slower at 490 million kilometers per year. Like Voyager I, it crossed the heliopause without a noticeable change in the magnetic field. However, Voyager II's crossing happened during a peak in solar wind activity, contrary to predictions based on solar cycles. These unexpected findings expose the limitations of our theoretical models and emphasize the importance of real-world data. As Voyager I and Voyager II continue their journey, they may encounter different magnetic orientations, but their instruments will likely be inactive by then. However, let's explore how far Voyager I can go and discover more beyond our solar system. To communicate with Voyager I, we transmit a 20 kilowatt signal from Earth using radio waves. It takes nearly 20 hours for the signal to reach the probe, and Voyager I sends data back to us with a much weaker 20-watt signal. The signal weakens as Voyager I travels through space, but we can still detect it using sensitive receivers. NASA's Deep Space Network, equipped with large antennas, listens for Voyager I's faint signals. With advancements in signal detection, there's no limit to how far we can communicate in space as long as our receivers are sensitive enough. Currently, only 4 out of Voyager I's 11 scientific instruments are still working, gathering important data about magnetic fields, solar winds, and cosmic rays beyond our solar system. However, due to the spacecraft's age, it is experiencing some malfunctions. In May 2022, something unusual occurred within Voyager I. Being in interstellar space presents significant challenges as it encounters cosmic rays and interstellar radiation without the sun's protective magnetic field. Suddenly, the spacecraft's signals began behaving strangely. It was like those bizarre sounds your car makes when you accidentally put in the wrong fuel. Scientists were scratching their heads, desperately trying to figure out what the heck was going on. Its signals started acting strangely, providing nonsensical data. The situation with Voyager I signals suggests that it's not pointing in the strange directions it claims, or else there would be no signal at all. Moreover, the signal strength remains the same, indicating that the direction hasn't changed. Upon investigating further, it was discovered that Voyager I's attitude articulation and control system, AACS, responsible for ensuring the spacecraft's antenna points towards Earth, is the system behaving strangely. The AACS stopped sending coherent data, which raised concerns. Curiously, Voyager I doesn't recognize any issues and hasn't entered emergency safe mode settings to shut down non-functioning systems. It believes that all its systems are working properly. The fault turned out to be with the AACS computer, which Voyager I had decided to use to send data back to Earth. However, the older, faulty computer corrupted the data, resulting in the strange numbers. NASA resolved the problem by instructing Voyager I to switch back to the correct computer. While this problem was resolved, it highlights the challenges and potential risks of further malfunctions as Voyager I continues its journey through interstellar space. In about 8 years, Voyager I will completely run out of power and won't be able to keep its instruments running anymore. Scientists will continue to communicate with the space probe and receive the important information it gathers until it eventually sends its last bit of data and disappears silently into space, never to be heard from ever again. So, although the end is approaching for the Voyager space probes, we can truly admire the remarkable journey they've undertaken and the valuable scientific knowledge they've provided us. And after all of this, Voyager I can quietly say, mission accomplished. It was launched the year I was born. It's truly amazing to see Voyager I still transmitting data. Long live the Voyagers! Just a reminder, while you watch this video, Voyager has traveled 4,630 miles. Thank you so much for spending time with me today. My name is El Laureate. If you enjoyed our interaction or gained any knowledge, I would greatly appreciate if you could support me by liking, subscribing, sharing, and commenting. Your engagement truly means a lot to me. If there's a particular story or topic you'd like to explore or learn more about, please let me know in the comments.